on the air again. It's March 16th. It's a Tuesday. It's a new stuff. Here we go. Power series. What is a power series? Well, here's an example of a power series. You ready? I don't know. Hold on to your hats. Here we go. So let's say I gave you sigma, right? It looks like a normal series, doesn't it? As k goes from 1 to infinity, right? Still looks like a normal series, doesn't it? Yeah, but now it's not. Okay, so it's not a series of constants, a bunch of numbers like a half plus a third plus a fourth, right? It's not that. It's a series of power functions. We're going to add up a bunch of power functions. So tell me, what do you get? Plug in 1. X plus x squared plus x cubed plus and so forth, right? Now the idea is that if this series converges, remember series last week of constants, sometimes they converge, sometimes they didn't, right? And they converge to a number. Now, if a power series converges, it converges to a function. Okay, and what's nice about this is if it converges to a function that's hard to integrate, or differentiate for that matter, this is easy. Because it's just power rule all over the place if you want to integrate. Okay, now the thing is though, there's an issue of convergence. Does it converge or not? If it converges, what does it converge to? What's the function? Also, how good is your estimate? Because this only converges if you add up infinitely many terms, right? It goes up to infinity. But you can't do that. So if you truncate it to 3 terms, 4 terms, 5 terms, how bad is the error if you're trying to estimate answers using it, like the area under a curve, like a definite integral or something? Yeah. Yeah, exactly. Assuming it converges to a function. And by the way, this does converge to a function, and you know what it is right now. Because isn't this a geometric series? What makes a series geometric? Whatever the first term is, you get the next one by multiplying by a common ratio. And next one by multiplying by the same thing. That's why it's common, the common ratio. What am I multiplying by to get here? What am I multiplying to get here? Is it the same thing? Yeah. So remember when we had, what was it, geometric series? A, r to the n starts at 0. So the first term was a, and then was a times r, then was a plus times r squared, and blah, 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 blah. Remember, first term over 1 minus the common ratio is what it converges to if it's geometric, only if the common ratio in absolute value is less than 1, right? All right, compare this to this. Who's a? A is the first term. What is it? X. And you told me the common ratio was, I'm multiplying by r, multiplying by r, multiplying by r, I'm multiplying by what? Okay, so this is a over 1 minus r. This thing, if you add up infinitely many terms, is this function. Okay, except there's an interval of convergence. As long as r in absolute value is less than 1. But remember, r was x, right? As long as x in absolute value is less than 1. Otherwise it blows up. So if you plug in numbers less than 1 in absolute value, like a half, this will work. If you plug in numbers bigger than 1, like 2, this won't work. 2 plus 4 plus 8 plus 16 plus 32 blows up, right? But what's nice here is now you have really infinitely many series of constants, like the series we had last week, where x can be any number between what? Well, what numbers are allowed then? Between what and what? If the absolute value of x is less than 1, what are the x values? What's the interval of convergence? What's the domain here? Can you plug in 0? Yeah. Can you plug in 1? Is 1 less than 1? No. Can you plug in negative 1? No. Can you plug in 2? Can you plug in negative 2? Can you plug in a half? Can you plug in negative a half? All right, so what are the numbers I'm getting? Between what and what? Not 0 and negative 1 and 1, right? This is the same interval right here. All right? This is an example of a MacLaurin series. A MacLaurin power series. All right, MacLaurin power series are always good at 0. Does this work at 0? If I plug in 0, does it work? Yeah. Or near 0, like this one, or for all real numbers, x. Okay? A MacLaurin series is a series in powers of x where the interval of convergence is centered at 0. Yeah? No, because it's to the k's. The k is never 0. Right? So it's k to the 1, to the 2, to the 3. So you don't get 0 to 0. Yeah, but I'm saying whatever, this one, right. But I'm saying the point is the first term is a, whatever it is. And the next term is times r, right. So, that's not really an issue here. All right, so what do we know about MacLaurin series? Already we know several things about MacLaurin series. MacLaurin series can be written, let's see. All right, this is a MacLaurin series in general. Will always look like this. Sigma, k goes from 0 to infinity. C sub k, x to the k. Okay, that's the general form. It's not just x plus x squared plus x cubed plus whatever. It could be some function in front, some constants in front. So it could be like, I don't know, c0 x times x to the 0 plus c1 times x to the 1 plus c2 times x to the 2 plus c3. Okay? So some constant plus some constant times x plus some constant times x squared. That's typically what a MacLaurin looks like. That's sort of like what we got here. All the constants in front were 1. Okay? So C1 is 1, C2 is 1, and this constant was 0. So this is a general form for MacLaurin. What's nice about MacLaurin is it converges only at x equals 0 or near x equals 0. So x is between two values, let's say negative r and r, or for all real numbers. Let's write it this way. Okay? Now what's r? R is the radius of convergence. What's 0? The center. All right? So on this interval of convergence, what's the center? 0. What's the radius? 1. Okay? All right, so all MacLaurin series will be centered at 0. They're best at 0. And they converge for usually for more than that, for at least a certain finite radius about 0, or for every real number. Now those are nice. The power series that converge for all real numbers, they're nice. But remember, that's only true if you add up infinitely many terms. So if you don't, it's still going to be something like this. The interval convergence will not be infinite, it will be finite, if you take finitely many terms. Okay, now this is very convenient. Now look, is that true? Let's graph this thing. Let's see what this thing looks like. Let's see what this thing looks like. And see that this looks like this only for these x's. Okay, here we go. Let's go to Hal. And I'm going to compare this function. I guess I'm in sequence mode, so I'm going to change my mode to function mode. Okay, let's go into y equals. And let's just graph x over, enter, x over 1 minus x. Okay, let's just zoom for that for now. And of course it has a vertical asymptote at x equals 1. So I have to find at x equals 1, right? Okay, now what does this series look like? Well, let's see. If I add on one term, notice that's a linear function. Isn't that like mx plus b, where m is 1 and b is 0? That's a linear approximation. That's probably the tangent line at 0. Let's see about that. See the tangent line? Okay, now tangent line approximations are very good near 0 because of local linearization. Remember local linearization? If you blow up a curve, a continuous curve enough, eventually it looks a lot like its tangent line. So near the point of tangency, the values on the tangent line, the y values on the tangent line, are very close to the y values of the function, so we use tangent line approximation sometimes. All right, but what if we make the approximation better? Let's add on another term. Whoops, where happened to my x? What happened to my, what is going on with the keyboard here? It's skipping. Hang on. Boom. Okay. All right, so now we're going to get some curvature here. Okay, let's see. So that's the original function. And here's my estimate to that function. All right, so now it's a parabolic estimate. And if you blow this up near 0 sufficiently much, you're going to find that the y values of the parabola are closer to the y values of the curve for more values of x than the line. Okay, let's add on some more curvature. Whoops. The next term was x cubed, right? All right, so add on another term. And here's the function we're approximating. And here's our MacLaurin, finite MacLaurin series, only 3 terms. And notice how before the parabola was approaching from above, now the cubic is approaching from below. But the radius of convergence is getting larger. Even though I only have a finite number of terms, only 3 terms, x plus x squared plus x cubed, right? If you blow this up, you're going to see that the cubic and the function are very close to each other near 0, but more than just near 0. And remember, what did we say? The most this is going to work is between -1 and 1. Let's see. Let's add a whole bunch of terms. All right, I'm getting tired of this. Isn't there a sigma? Where the heck is that? Yeah, but isn't it maths or someplace? Math. Oh, gosh. Not there. Sequence? Some sequence? You could do it that way, but there's an actual sigma in here somewhere. Oh, screw it. It's in calculus? Oh, okay, all right. So math and calc. That's way down here. All right, and sigma. There you go. Okay, sigma. All right, let's do, whoops. Let's get rid of all that stuff. Okay, so I'm going to sigma x to the n, let's say alpha n, with respect to alpha n, from, what is it now, 1 to infinity, right? So from 1 to 1 would be just that first term, the linear term. Okay, if you plug in 1, that's all I'm saying. Plug in 1, you get x, right? So you're going to get that tangent line thing again. Or not. There it is, right? So we're getting the same stuff, okay? Alrighty. Then in y equals, change it up a little bit, make that go to 2. You'll get the parabola. To 3, you'll get the cubic. All right, let's go back to the cubic. There it is. Now, let's use ludicrous speed because it's getting slow. And let's undo ludicrous speed because then it goes into sleep. All right, that's where we left off before when we wrote it out. X plus x squared plus x cubed, right? Okay, now let's change it up. Let's go crazy. How about we tell it, I don't know, 10 terms. I don't feel like typing out 10 terms, do you? X to the 1 plus x to the 2 plus x to the 3 all the way up to x to the 10. You don't have to type it. There it is. Okay, so graph. And, of course, ludicrous speed. And this is really slow, but there you go. All right, it's done. You see what's happening? It's approaching from above, but look where it hugs the curve. It's indistinguishable from the curve here. And then it diverges near -1. Of course, it's going to blow up at 1 because the function blows up at 1. So do you see how the interval convergence, even graphically, it looks like it's only from -1 to 1? From x equals -1 to 1. This has nothing to do with it, right? My power series had nothing to do with this. So the power series doesn't estimate this. And my power series doesn't estimate this. It blows up. It goes to positive infinity over here. And it goes to positive infinity over here. But the function did too. So it couldn't converge at 1. But it doesn't converge at -1 either. But between. Are we good? Did you see why it's between? I can make it go even crazier. Whoops. Okay, let's go crazy, baby. I don't know. Can this thing handle it? Can you handle the truth? I don't know. Wait, let's do a graph. I'm going 100 terms. Oh, God. Okay, come on, come on, come on. You can do it. It's just 10 times more terms. Because I'm in the Zoom 4, which is friendly. Are you in Zoom 4? Really? Well, maybe I went a little too crazy. Where the hell's the function? Where the hell? There's the function. Where's the power series? I don't know. Oh, well. It'll show up somewhere. Yes, it's on ludicrous speed. There it goes. Oh! See, we didn't get much better than before. It's still hugging the curve. I better turn off ludicrous speed. It's still busy, but it's still busy? All right, fine. It's still hugging the curve for x values between -1 and 1, but at -1 it starts going flaky.
You know what? We've got a really small number, don't we?
Small number of what?
Like x, like 0.00.
Right, and then you're taking the 100th power.
That's gonna.
It's going to challenge the floating point processor, yeah. All right, so you know what? Just stop it already. Okay. Okay, you get the idea. All right, so graphically and analytically, we can talk about power series convergence. Okay, so how do you generate a power series? Well, if it's geometric, it converges for absolute value of r is less than 1. I can't hear you. This is MacLaurin, right? MacLaurin is always good at 0. That's not very interesting because if you plug in 0, guess what you get? 0. That was silly. But it's always good at 0. It's usually good near 0 if you add up infinitely many terms. Or sometimes it's good for all x. How about this one? Take a look at this power series. Let's say I gave you sigma as k goes from 0 to infinity of k to x to the k over k factorial. All right, now who is this? Well, let's plug in 0. What do you get if you plug in 0? Something to the 0 is 1, and 0 factorial is 1. Remember we talked about this. Pascal's triangle doesn't work otherwise. Okay, plus, plug in k equals 1. X to the 1 over 1 factorial, plus k to the k is 2. Plus k is 3. And so forth, right? X to the 4th over 24, and blah, 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 blah. Okay. All right, now my question is, if this converges to a function, I don't know even if it does, what's the interval of convergence? Now again, it's MacLaurin, so you know it's good at 0. All right, what's this here? Okay. Mariam, you've got mail. Oop, there's another one. Not for you. For Ethan, you've got mail. Ethan Lusterman, you've got mail. Okay. All right. Anyway, so I don't know what this converges to. See, that's a difficult question. Given the series, do you know what it converges to? What function? I don't know. This is backwards. Usually what you do is this. You're given a function, you're generating its power series, and then you're testing for convergence, okay? So last time, just because it was a geometric series, we knew what it converged to. That's rare, okay? This, I don't know what the heck it converges to. But what's the interval of convergence? What I want to do here is sort of like a ratio test. Remember the ratio test? Let rho equal the limit, as in this case k goes to infinity, of u sub k plus 1 over u sub k. But I'm going to get a little bit more fancy here. I'm going to use what's known as the ratio test for absolute convergence of power series. Now remember, if you have an alternating series, where sometimes you're really adding, then subtracting, then adding, then subtracting, that's easier to converge than if you're just adding, right? So sometimes you have weird signs and stuff going on around here. I don't want to deal with that, so I'm going to take the absolute value. But what I'm testing then is for the absolute convergence, which is a tougher test to pass, all right? Now remember, when do you have convergence? When rho is what? Less than 1. We're going to force the issue. We're going to solve this inequality for this u sub k. I'm going to find the values of x that make this less than 1. Okay? That's the ratio test for absolute convergence of power series. Okay? We're going to force it to be less than 1. Find out the x's that work there. Okay? And this, it sounds like it's insanely tough, but it's not. Okay, you ready? Do the same thing like we did before. U sub k plus 1 means do what? If this is the rule, u sub k is like f of x, right? But u sub k is a discrete variable, that's all. So this is the function right here, u sub k. So what is u sub k plus 1? Plug in k plus 1, that's all. And then how do you divide by u sub k? Well, since it's a fraction, multiply the reciprocal. All right, so that's what we're going to do. We're going to say, all right, let's find the limit as k goes crazy of x to the k plus 1 over k plus 1 factorial times the reciprocal of u sub k, k factorial over x to the k. And we want to know when that absolute value is less than 1. And this sounds like the most insanely difficult inequality you've ever seen in your life. But no, you don't need help for this. Nope, you don't need help for this. Believe it or not, it's not that tough. Look, we've talked about this. This is why we did all this stuff last week. What's k factorial of the k plus 1 factorial? K plus 1, right? Like 5 factorial into 6 factorial leaves 6. What's x to the k into the x to the k plus 1? X. So what's the limit as k goes to infinity of x over k plus 1 in absolute value? Well, now realize that x is not the variable here. X is some number you're plugging into the power series, and you want to see if it works the same as if you plugged it into the function. So x is really a constant, it's some number. The variable here is k. So this is some number. As k gets humongous, what happens to this thing? It goes to 0. Is it less than 1? If this goes to 0, is it less than 1? Yeah. Does it matter what k is? Does it matter what x is? No. So here's your interval convergence. Any number you feel like. All real number. Okay? This power series, whatever it converges to, whatever function it converges to, a power series when it converges to a function, converges for every single x you feel like. That's a powerful result. Who is that function? That's a good question. Who is that function? Well, MacLaurin came up with this theorem. Can I move on? Everyone got that? Okay. This is MacLaurin's theorem. F of x, some function you want to get a power series for, okay, can be approximated this way. F of 0 plus f prime of 0 times x plus f double prime at 0 times x squared over 2 plus f triple prime at 0 times x cubed over 3 factorial. Okay. And so forth. Plus, 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 plus the nth derivative at 0 times x to the n over n factorial. This is MacLaurin's theorem. MacLaurin theorem for generating power series of the type MacLaurin. There are other types. We'll get to Taylor's series soon enough. Okay, so let's try this. This is actually not that difficult to generate a series with this. What if f of x is e to the x? Can you get me a power series for e to the x? Damn it, I can't write. Let's see. Dun, 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 dun. Okay. Yeah, 2 factorial is 2. Technically, this is 1 factorial. This is 0 factorial, isn't it? Technically, right? Okay, so what do you need? You need f prime, f double prime, f triple prime? All right, let's do that. Well, that's why I picked it. This one's easy. All right, so what's f prime? Wow, that was tough. What's f double prime? Well, geez, you're good at this. What's f triple prime? How did you know? All right, now they want you, and I can keep on going as many terms as I feel like. What the idea is to get some kind of a pattern, see if we can write it as a sigma. All right, now they want you to evaluate f and f prime and everybody at 0, right? Why? Because MacLaurin is good at 0. All right, so what we're really trying to do is trying to get the tangent line at 0. If it's increasing or decreasing, trying to put in some concavity, try to throw in the jerk, and so forth. Well, actually, this is the increasing, decreasing. This is the concavity. This is the jerk. You're getting more and more curvature, getting closer and closer to what the function looks like. So what's f of 0? Plug in 0. What do you got? Nobody knows? 1. Okay, guess. What's f prime of 0? 1. What's f double prime of 0? Wow, this is tough. Okay, and so forth. So what are you getting? 1 plus 1x plus 1x squared over 2 plus 1x cubed over 6. Does this sound familiar? This is e to the x. That's what this is. You just proved that the power series for e to the x converges for all real numbers. This is a powerful result. Not only do you know how to generate a power series for a function, in this case e to the x, there it is, but you can test for its interval convergence. Remember, if it's a series in powers of x, that's called the MacLaurin series, it's good near 0, it's good at 0 or near 0 or everywhere. Well, guess what? It's good everywhere. But what's the center of convergence still? What's the center right between? It's still 0. Okay? Remember, it's good at 0 or near 0 or everywhere. But the center of convergence is always 0, right? For MacLaurin? And the radius is infinite. Right. All right, so if we wanted to write e to the x, we would say it's f of 0 plus f prime at 0 times x plus f double prime at 0 times x squared over 2 plus f triple prime at 0 times x cubed over 3 factorial plus. Well, what did we get? We got 1 plus 1x plus 1x squared over 2 plus 1x cubed over 3 factorial. So what is it? Sigma as, x to the k over k factorial. K starts at 0. All right, so this is going to be a little art form here, getting from this pattern to this pattern. Do you see it? Isn't it powers of x? X to the 0, x to the 1, x to the 2, x to the 3. Isn't it over factorial? 3 factorial, 2 factorial, 1 factorial, 0 factorial. So this is a little art form here. We've got to see this pattern as a sigma. And when is this true? When is e to the x equal to this? For all x. So this is the game we're going to be playing. Given a function, can you generate the series? Is there a pattern? Use that pattern with the ratio test to see the interval convergence. Okay? Let's try it again. Can you get me MacLaurin for sine? MacLaurin series for sine. Let's see. What if f of x is sine x? What's f prime? Cosine. What's f double prime? Negative sine. What's f triple prime? And so forth. I think I'm going to need a couple of more terms. You'll see why in a minute. This becomes sine, and this becomes cosine. Notice these things up here are Roman numerals, by the way. Okay, and if it's 0, it means no derivative, just the function. Okay, but of course Rome didn't know about 0. Anyhow, so we're trying to do MacLaurin, so we need f of 0. What's the sine of 0? 0. And what's f prime of 0? What's the cosine of 0? 1. And what's f double prime at 0? What's the negative sine of 0? 0. What's f double prime, triple prime at 0, or negative cosine of 0? Negative 1. What's quadruple prime at 0? 0. And what's quintuple prime at 0? Damn it. And it's back to 1. Okay, so let's write the series. Remember, f of x is going to be f of 0 plus f prime at 0, x plus f double prime at 0 times x squared over 2 factorial plus f triple prime at 0 times x cubed over 3 factorial plus. So what did we get? Sine of x is, all right, now the f of 0 was 0. So this term drops out. And f double prime drops out. And f quadruple prime drops out. So focus only on the odd powers. All right, this was 1, this was negative 1, and this is not going to repeat. 1, it's going to be negative 1 again. Okay? So I'm getting 0 plus 1x plus 0 minus x cubed over 3 factorial plus 0. What do you think the next one's going to be? X to the 5th. The evens are dropping over 5 factorial plus 0 plus, what's the next one? And it's going to be negative, right? Because it's changing sign? Okay. So, okay, you get the pattern, don't you? Let's condense this a little bit. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. I can't write today. Plus, plus, plus. Okay. Can you write that in terms of sigma notation? Ethan. Well, x to the n plus 2, if n is even, that would be even. If n is odd, that would be odd. That's not going to help. 2n plus 2 is still even. 2n is even. I need odd powers. 1, 3, 5. You're on the right track. This is what we have to decide. 2n what? Or plus 1. Either way. All right. Over the same thing, factorial. Aren't all the exponents the same as, right? 3 factorial, 5 factorial, 7 factorial, right? Aren't they the same? Sigma starts at n equals what? 0. If I plug in 0 here, I get 1. 1 factorial. Plug in 1 here, I get 3 factorial. If I plug in 2 here, I get 2, what? 5 and 5 factorial. Right, that's good. But what about the plus minus plus minus? Yeah. Negative 1 to the n. If n is 0, that becomes positive. N is 1, that becomes negative. N is 2, that becomes positive. N is 3, it becomes negative. Perfect, that's it. Now, what's the interval convergence? Remember, it's MacLaurin, so it's good at 0 or near 0 or everywhere. Which is it? Well, let's do a ratio test. I want the absolute value to be less than 1 in the limit. Remember, u sub n plus 1 over u sub n. Now, the absolute value obviates this, so don't worry about this. Drop it. What if we plug in n plus 1? What's 2 times n plus 1? 2 times n plus 1? No, times. 2 times n plus 1. I'm plugging in n plus 1. 2n plus 2 plus 1, right? All right, so I got x to the 2n plus 3 over the same thing factorial times the reciprocal. What's convenient about the absolute value is you don't have to worry about this, and you get an interval. Because if an absolute value is less than 1, you get a certain interval. Okay. So what's nice about this is that you know how this reduces. 2n plus 1 factorial into 2n plus 3 factorial is what? Well, let me give you a hint. It's like 5 factorial into 7 factorial. Isn't it 2 more? 1, 3? So if this is 5 factorial and this is 7 factorial, what's left? 7 times 6. 5, 4, 3, 2, 1 canceled, right? So what's left? 2n plus 3 and 2n plus 2. Okay. What's x to the n plus 1, 2n plus 1 into the 2n plus 3? X. Nobody knows? This into this leaves x what? Squared. In absolute value, that quotient's got to be less than 1 in the limit. But guess what? This is a constant. Something we're plugging into the function. This is going crazy. So what's this limit? Some number over n to the going to infinity, n squared, no less. It goes to 0, just like last time. So did it matter what x value you picked? So any x value is good. Yeah, so this is also an infinite radius of convergence. This is rare, but it happens. Alrighty. You know power series for e to the x and sine x. You know the convergence test for absolute convergence of power series. Ratio test for absolute convergence of power series. You know what a MacLaurin series is? You know a lot. Yeah, let me just stop this stupid